Okay, we have seen previously that the energy stored in a capacitor is, the potential energy in a charged capacitor is 1/2 Q squared over C, which, because C is defined as Q over delta V, also equals 1/2 Q equals C delta V. So we have a C delta V squared over C, which is delta V squared over 2C. And also equals, whoops, that was wrong. Did that math wrong. That's CV squared, 1/2 C delta V squared, which also equals 1/2 Q times delta V. So we've seen this before, that the potential energy stored in a capacitor. This was derived by showing how much energy it took to move a single charge from through an electric potential, and then integrated over all the charge that moved through the potential. So the total charge that is moved through the potential is Q or minus Q, right? Total charge of plus Q must have been taken from one plate and moved to the other plate through a potential delta V. So this is generally true. It's not true just for a parallel plate capacitor. It's generally true. Now, how does this relate to the potentials and potential energies we've talked about before? Well, we've talked about the potential, the electric potential due to a point charge. We've talked about the electric potential due to a line of charge. And we've talked about the electric potential due to a sheet of charge. And when we talk about the electric potential, right, the electric potential, these are three independent situations. We're talking about what is the potential to give another charge some energy if that charge is some distance r away at point P, r away at point P, etc., r away at point P. And so what we do in that case is we say, therefore, the potential energy, this is just a real review, right? The potential energy, if we actually put a charge at point P, if we put a test charge, we call this guy the test charge, right? If we put a test charge there, we know that the potential energy, U, is equal to Q times the potential at that point. I guess it could be delta V, because we're measuring that potential relative to some V equals 0, or we would just write that as QV, understanding that V is measured relative to some V equals 0. So that's for a point test charge in a potential in general, right? So this is the general equation we knew. So how does that relate to this? Well, this is, now what we're doing is we're not putting a point charge in a potential. We're putting a collection of charges in a potential. So this is the potential energy of a collection of charges, right? This Q now is a collection of charges that is in a potential. That's in a potential difference, or in a potential. So this is generally, we talk about this in the box. That's the potential energy in a capacitor. So for example, if we've got a parallel plate capacitor, it's the potential energy of all the charges on one plate in the potential of the other plate, right? So previous to this, we just talked about the potential of a single charge in the potential of the other plate. Now we're talking about of all the other charges in the other plate. So that's why we're talking about the potential energy, why the big box at the top is the potential energy in a capacitor, because we've now taken a bunch of charges and we've separated them. And that's what a capacitor is. It's something that holds a charge separation. So anyway, so this is the potential energy in a capacitor. So let's say, for example, let's just do a quick example. Let's say that we've got a parallel plate capacitor, let's say it's a parallel plate capacitor in a circuit, and let's just build a circuit here. Let's put a parallel plate capacitor in that circuit. Let's say that we've got a 9-volt power supply, and the capacitance is 1 microfarad. And so let's just ask, how much potential energy do we store in that capacitor? And the reason, and remember what a capacitor is, it's an electric field energy storage device, right? So if we take the battery away, the capacitor by itself, if it's already been charged, if we have plus Q on this plate and minus Q on that plate, if we take the battery away, then it's still holding the energy, and that can be used for something else. So it can be used as a battery source, for example. We talked about that before. So let's say how much energy is stored in this capacitor. Well, the energy is 1/2 Q delta V. We can write down any one of the forms of the equation. I don't know what Q is. We can figure that out, but it's also equal to 1/2 C delta V squared. And here we already know C and delta V. The potential across the capacitor is 9 volts because the battery is connected only to the capacitor. So therefore, U is equal to 1/2 times the capacitance, 1 microfarad, times delta V, which is 9 volts squared. So we've got 81 over 2, which is 40.5 microjoules. This is going to be farads times volt. Now, farad times a volt is an energy. It's MKS units, so that's going to be joules. 40.5 microjoules. So it's not a lot of energy. It's a little bit of energy. Remember, this holds true for any kind of capacitor. It doesn't have to be a parallel plate capacitor. So if the capacitor in the circuit diagram were a cylindrical capacitor or a spherical capacitor or anything like that, capacitor is any two conductors near each other. This still holds. Nothing's different here. So it looks like this is a small amount of energy. Let's just compare it to, let's think about when we had a mass. Let's make a 1 kilogram mass and we lift that up to a height of 1 meter above the ground. What is the energy, the potential energy of the Earth mass system, right? There's a potential energy due to the fact that there's a separation between the Earth and the mass, just like there's a potential energy due to the fact there's a separation in the charge in the capacitor, is mgh, which is going to be 9.8 joules, right? 10 joules approximately. So how would we get 10 joules in a capacitor? Could you get that much energy stored in a capacitor? Could you have a capacitor that had enough energy to lift a 1 kilogram mass to a height of 1 meter? Well, remember that a 1 farad capacitor is big. They actually do exist. We can get 1 farad capacitors. They're pretty special. They're not very expensive, but they're unusual. A millifarad is more like a standard sort of large capacitor. So let's just say we have a capacitor of about a millifarad. So therefore, how much potential difference would we need, right? Your potential difference would have to be, well, if U is equal to 1/2 C delta V squared, therefore delta V, I'm going to write at the top so that I don't have to go to the next. Delta V is the square root of 2U over C, solving for delta V, plugging in the numbers. So that ends up being 141 volts. So that's not unreasonable. You can get 10 joules stored in a capacitor, a 1 millifarad capacitor, by putting 141 volts across it. Remember that the wall outlet is about 120 volts AC. It's not unusual to be able to get 141 volts. Bigger than your standard battery, but still not unreasonable. So let's do another energy in a capacitor problem. Let's say I hook up a circuit with a 2 nanofarad capacitor. Again, doesn't need to be a parallel plate capacitor. You just draw them as parallel plates in a circuit with a 2 nanofarad capacitor, and I hook up a 3-volt battery, 3-volt power supply. So I'm going to ask a couple questions. Let me write them down. Okay, I'm going to ask 3 questions. What is the charge on the capacitor? What is the energy stored in the capacitor? And if I add a dielectric between the capacitor plates, does the energy go up or down? Okay, so let's see. A, what is the charge on the capacitor? Well, we're just going to use the definition of capacitance. C is Q over delta V, and therefore Q is equal to C delta V, which is 2 nanofarads times delta V, which is 3 volts, the voltage across the capacitor, which is 6 nanocoulombs. Don't forget to carry the prefix 6 nanocoulombs, and that's 6 times 10 to the minus 9th coulombs. What is the energy stored? B U is, you can use any of the three formulas because we know C, delta V, and Q. I'm just going to use, let's say, 1/2 Q delta V, and the energy stored is 1/2 times 6 times 10 to the minus 9 coulombs times delta V, which is 3 volts, which is 9 times 10 to the minus 9 joules. Okay. Now, if I insert a dielectric between the plates, does the energy go up or down? Well, if I put a dielectric in between the plates, what I'm going to do is I'm going to fill the plates. Choose a color here. Hold on. Let's go ahead and fill the plates with water or something. Doesn't matter, plastic. Doesn't matter what the dielectric constant is. Does it go up or down? Well, it may be obvious. It may not be. Let's just take a look at the energy formula that we used, 1/2 Q delta V. The delta V doesn't change because the delta V is defined by the battery. Q, does Q change? Does Q stay the same, go up or go down? Well, Q goes up because what the dielectric does is it allows you to store more charge on the capacitor. So Q goes up, so therefore, since Q goes up, therefore U goes up because delta V is the same. The other way to see that is that you know really what dielectric does is it increases the capacitance. That's why it increases charge. And the energy in terms of the capacitance, going back to the formula, the energy in terms of the capacitance, going back to the formula, the energy in terms of the capacitance is here, right? So the energy is 1/2 C delta V, and delta V is the same, doesn't change because it's attached to a battery. C goes up, so U goes up. Let me take the same situation and just talk about what happens if I take the battery away. Let's charge the capacitor. So we're going to charge the capacitor. And we figured out in the previous page that Q is equal to 6 nanocoulombs. Q equals 6 nanocoulombs. Then detach the battery. So this is the situation we have. We have a capacitor that's charged with 6 nanocoulombs on one plate, plus 6 on one plate, minus 6 on the other plate, doesn't matter, 6 nanocoulombs, and the capacitance is 2 nanofarads. Now, let's say, and remember that the energy, we figured out the energy stored. That's going to be relevant because of the question I'm about to ask. The energy stored was 9 times 10 to the minus 9 joules. If U is 9 times 10 to the minus 9 joules, we figure that out. If I separate the plates more, in other words, pull them apart, does U stay the same? Increase? Oh, shoot. I'm not sure. I wasn't recording and I thought I was. So I'm not sure what you heard. But anyway, here's the problem that we're solving. So we've got the capacitor, we charge it, we detach it from the battery. We had already figured out the charge and the energy. Forget the dielectric, we're just no dielectric here. If I then move the plates farther apart, if I move the capacitor plates farther apart, does the energy stay the same, go up or go down? Think about that for a second, pause it, think about it, but I will go on. What happens is the energy, think about it. So the plates, are the plates, let's just say that these were actually two plates that were free to move. Would they be likely to move together or move apart, right? So they're attracted to each other because one plate is positive and the other plate is negative. So they're attracted to each other. So it takes me work to separate them. So if I have to do work to separate them, do I increase the potential energy or decrease the potential energy? Just like if I do work to lift a mass off the ground, do I increase the potential energy or do I decrease the potential energy? Right? So I must increase the potential energy. The answer here is increase, that the potential energy of the situation must increase. Let's see why that's true. It's because I do work to separate the plates, because I have to do work on the system. I have to add energy to the system. Doing work on the system adds energy to the system. But we can see why it's true by looking at 1/2. I'm just going to write down one of the formulas, Q delta V. Let's say, for example, well, Q has to stay the same. Ah, wait, but we don't know what happens to delta V. Delta V does not have to stay the same because it's no longer attached to the battery, right? So the charges can't flow on or off, so delta V does not have to stay the same. So we don't know what happens to delta V. So let's go ahead and look at one of the other formulas. I'm going to go back and Q squared over C, let's say. Whoops. 1/2 Q squared over C. Aha. So here's one. We know that Q must stay the same because no longer attached to a battery, the charges can't go anywhere. So Q stays the same. And what happens to C? As we increase the space between the plates, the capacitance goes down, right? The capacitance goes down as we increase the distance between the plates. The capacitors go as the inverse of the distance. So the fact that the capacitance goes down means that the energy goes up. Okay. And that means also that delta V goes up. Okay, so these arrows over here meant this is the same, and this goes up. Okay, those arrows were just pointer arrows as opposed to going up or down. So the potential energy goes up if we separate the plates. Okay.